We are now going to discuss a topic called Big O. Big O is a notation used to classify how scalable an algorithm or function is, and it allows us to estimate the worst-case runtime of an algorithm, or how long it takes the algorithm to complete, based on the input size. So what this means is that Big O informs us of how much slower an algorithm will run if its input size grows. If the input size gets larger, say an array of 100 elements instead of an array of 50 elements, will the runtime of the function stay the same? Will the runtime get proportionally larger as the input size increases? Will the runtime get exponentially larger? Or will the runtime change in some other way? This is what Big O notation tells us, and it describes how performant a function or an algorithm is. Let's do an example to help us visualize how Big O works. If we have a function called log that simply takes in an array and logs out the first two elements in the array, what is its Big O notation or runtime going to be? The runtime of this function is going to be constant, which we write as O of 1 in Big O notation. We know that the runtime is constant because as the input size increases, or in this case, as we increase the size of the array, the number of operations that we perform never changes. We still only log out the first two elements, no matter how large the array gets. This is called constant runtime and is written as O of 1 in Big O notation. We can see this visualized on this graph. As the input size increases, the x-axis, the time that it takes to run the function never changes, which is on the y-axis. Let's do another example. Now we have a function called log_all, which takes in an array and logs out every element in that array. What is the runtime of this function? Well, we know that we have to do an operation on every single element in the array now. So as the input size increases, our runtime will also increase. For this function, our runtime will increase proportionally to how much our input increases. And that makes sense, right? If our array has 5 elements, we will have to perform 5 operations, or log it out 5 times. If it has 6 elements, we will have to perform 6 operations. If it has 7 elements, we will have to perform 7 operations, and so on. This is called linear runtime because the runtime is proportional to the input, and we write it as O of n in Big O notation, where O stands for the function we are evaluating, and n stands for the size of the input. Let's run through 2 more runtimes, or time complexities, that are very often seen throughout engineering and programming, and that we will come across in this course. The next runtime that we will explore is exponential runtime. So now we have a function called add and log, which takes in an array. What it does is it gives us every possible combination of pairs in the array. It iterates through the whole array, but on every element that it hits, it goes through the whole array and hits on every element again, so all possible pairs are made. That's why we have 2 nested for loops here. So, for example, if we have an array of 3 elements, we have 9 pairs that are logged out. And if we have an array of 4 elements, we get 16 pairs logged out, and so on. This is exponential. As we add 1 element to the input, the runtime makes an exponential jump. You can see this visualized on the graph, and you can tell that this is not very efficient or performant. If you write a function like this in your code, you probably won't be able to notice the performance issues with very small inputs, but as your inputs start to scale and become very large, a function with exponential time complexity becomes very inefficient and can slow down an application. So we try to stay away from creating functions that have this runtime as much as possible. And exponential runtime is written as O of n squared in Big O notation. Now, the final runtime that we will explore is logarithmic runtime, and it is very performant. An example of a logarithmic algorithm is binary search, and you can see the code for this over here. Now, instead of running through this code, let's think about it conceptually. In any binary search algorithm, we will have two inputs. One is a list that must be sorted in some way, either numerically from least to greatest, or from greatest to least, or alphabetically, etc. It has to be sorted in some way. And our other input is simply just a single value that we want to try and search for within our array. Binary search has a logarithmic runtime because with every operation that we perform, we are cutting the input in half. This is great because even if we have a huge input, we are only going to be looking at a fraction of the elements to find the one that we are searching for. Let's take a real-life practical example of binary search. If you had a physical dictionary and you wanted to find a single word in that dictionary, you would find it by doing binary search, probably without even realizing it. Let's say that you are looking for the word house in your dictionary. You would open up the dictionary to the middle, and you would notice that you are in the M section. Well, you know that house will be before the M section, so we can totally forget about the second half of the book. So we just cut our input size, or the number of elements that we have to search through, in half. We are now left with the front half of the book, so we will go into the middle of this section, and we will notice that we are now in the F section. We know the word house will be after the F section, so we throw away F and everything before it. So we just cut our input size in half again. We are now left with sections G through L. We go to the middle of what we have left and we wind up in section I. We throw away everything after I because we know house will not be in that area. We go to the middle of what is left and we are now in the H section, and we have successfully found the word house. This is essentially binary search, and you can tell that it is efficient because we only performed about 4 operations to find what we were looking for when our input had 26 elements. As our input size grows, the number of operations that we will perform will not grow proportionally, but it will grow logarithmically. If we had an input size of 4,000 elements, it would only take us about 12 operations to find the element that we are looking for. This is really powerful and really efficient. Binary search is an example of logarithmic runtime or time complexity, which is written as O of log n in Big O notation, and you can see it depicted on our graph. That is it for our introduction to runtime and Big O notation. Now that we know what time complexity and Big O notation are, let's code out our harmless ransom no algorithm. There is a way to code it out in exponential time complexity, and there is a way to code it out in linear time complexity. Obviously, we want to do what is more performant, so we will build it in linear time complexity. Let's get started in the next video. See you there.